Having said that, I'm very pleased to introduce Chenyang Xu, who will give his first talk on K-stability and Moduli of Fano Varieties.
Thank you very much, Gabby. So I started to attend SRI from 2005 in Seattle. And in both Seattle and Salt Lake City, I stayed for like 3 weeks. I think it gave me a unique chance to somehow view algebraic geometry as a global subject which unifies lots of different topics. So I really hope that the young people here, especially students, would have the same feeling with this conference. So I'm going to talk about K-stability and the Moduli of Fano Varieties. So it's largely a story happened in the last decade, and it consists of contributions from many people. So I'm very honored to be invited to give a chance to speak on this. So today I will talk about the Moduli of varieties, the definition of K-stability, and also the K-stability valuations. So, of course, for our algebraic geometers, we are interested in moduli. And usually when we talk moduli, I mean, there are two types of basic objects. One is moduli of varieties. I mean, one is moduli of like sheaf-like objects. So for this talk, I will mostly concentrate on the first one. It's moduli of varieties. So roughly speaking, basically for a class of varieties, I want to construct a space M, which plays like a map, like a moduli, such that each object in the X in this class precisely corresponds to a point. I mean, the toy example is Grassmannian, which basically parameterizes linear k-dimensional linear subspace in Cn. A more complicated example, which is probably also, I mean, the starting point of the modern moduli theory is Grothendieck. He constructed the Hilbert scheme, which parameterizes subschemes of Pn. So he doesn't just parameterize those objects abstractly. He actually parameterizes how the object is put into Pn. But for us, we are more interested in parameterize objects abstractly. So basically the isomorphic classes. So for that purpose, there are two steps. First, we need to embed our object into Pn by some like polarization, some unpolarized bundle. And as you know that there is no canonical choice of X into Pn. It's always up to a choice of basis. So in other words, you have to allow PGN+1 acts on the Pn and move your X, and you should view this orbit as 1 point. So in other words, you have to take a quotient. So to treat the first issue, if we want to put our X into Pn, we have to pick up a polarization. And for variety, essentially there is only one family of natural polarization, which is given by the tensor power of omega x. So here the tensor power could be either positive or negative. I mean, omega, of course, is the dual of the highest wedge of the tangent bundle. So with all this, now we enter the first phase of the construction of moduli of varieties, which is moduli of curves. I mean, historically, of course, there is a long history of people trying to parameterize varieties going back to Abel, Jacobin, Riemann, Weierstrass. And Teichmüller was the one who first had an analytic theory to really parameterize curves with higher genus. But the algebraic theory, I think no doubt was started from Mumford. So basically he constructed the MG, which parameterizes higher genus curve. So here higher means at least 2. So basically he's used this machine called the geometric invariant theory. And then later, during Mumford, they constructed this MG bar, parameterizing a compact modular space with nodal singularities. So here, basically the limiting object is a curve such that it has nodal singularity and omega c is still ample. So actually, if you go to the proceedings of the Woods Hill, I mean, Mumford, the lecture name of the name of the lecture given by Mumford is called the boundary point of moduli. And if you read his notes, he said, I mean, basically he listed the status of constructing the boundary of the moduli. Like there is one case he said very good, that's for vector bundle, and pretty good for moduli of curves, and okay for polarized abelian variety, and no good for abelian for general type surface. So that time clearly Mumford was thinking about it, but he didn't have idea of how to treat the limit point. And this comes to the second phase of the moduli theory, which is the moduli of varieties with K positive, but now it's in higher dimension. So for instance, like a surface. So for this goal, if we look at the open part, we should include all smooth X with ample Kx. However, the difficulty, as Mumford already noticed, lies on characterize the limit. So basically, the Mumford's GIT doesn't work in this case because, I mean, the natural way, if you choose omega x, you embed x into Pm, then the GIT limit will depend on the choice of M. When M gets larger and larger, there is no stable limit. I mean, this was somehow expected like 40 years ago, but it was proved 10 years ago. So there was like no real stable limit. I mean, no wonder Mumford think that constructed limit in the general type case is a difficult question, at least from the GIT perspective. But however, the theory which really works in this case is the so-called KSB or KSBA theory, standing for Koller, Schiffer, Baron, and Alexeev. So roughly speaking, I think you will hear this more in the Friday lecture given by George. But roughly speaking, the KSB stability is just for varieties with still omega x is positive and some mild singularities. So, however, how do we get this limit? It's very different with GIT. Actually, the limit is given by the relative minimal program. I mean, I think that was what Koller and Schiffer-Baron noticed in their famous 88 papers. Somehow, I think that time the minimal program was still a newborn theory, but they realized that you can use it to study moduli, especially for moduli of general type varieties, and to find the limit. So let me briefly mention that by late 2010, the construction was essentially completed. And one of the reasons why we have to wait so long is to construct this, the process is intertwined with the progress of minimum program. You really need the foundational results like the BCHM and many other stuff to finish this. But there's one foundational notion in the theory which we will also need, but we will really not talk about it, is something called the local K-stability theory. So basically, it just give a right notion of a family of higher dimensional varieties over a general base. If you think about this is actually quite subtle. I mean, because we allow singularities on your varieties, but we don't want, for instance, embedding points show up, at least on the underlying variety. So somehow there is really an interplay between you want to allow certain singularities, but then you still have to show that the class you work on is small enough that you don't, some bad behavior will not happen. Anyway, fortunately, all this is worked out by Koller. I mean, this is his book, published in 2023, I think. And this general notion of family of varieties is actually far more subtle than flatness. So in the curve, we just require that we have a family of curve, every fiber is stable. But this family, when I say family of curve, we mean flat family of curve. But in general, I mean, higher dimension, we actually require that we work on a local K-based stable family of varieties, such that every fiber is stable. So we replace the the flatness by the words of local stable, which is a far more subtle notion. But this is workout, so we need it, but I'm not going to talk about it. Then we enter the third phase, which is how about the Fano varieties. So of course, Fano varieties is the case that with the minus kx example. And as we know that this belongs to one of the trichotomy of classified varieties by just simply looking at the sign of the kx. So you can allow kx to be either positive, 0, or negative. So this is the case when x is negative. And we all know that in dimension 2, if we look at the final surface, which is called the Pearl surface, at least for the smooth one, there are only 10 families of them. I mean, if you read Hartman, you probably know this result. And a similar result is known for dimension 3, but it's much more recent. I mean, well, not that recent, but still 40 years ago, that we basically can classify all the smooth family of Fano threefolds, which there are 105 deformation families. And classical result by Miyakamori says that if you fix any dimension and look at all smooth Fano varieties, then they vary in a finite the number of families. So of course, by now we know much stronger boundaries result than this. But at least this gives you a feeling that if you want to work on Fano varieties, smooth Fano varieties for a given dimension, you actually basically work on a finite many of families. And also, I mean, the Fano, historically, the Fano varieties, we know it has a interesting rich geometry. I mean, it has been studied from many different viewpoints, like rationality, like birational automorphism, Morris theory, I mean, cohomology and derivative category, and so on. I mean, I think you have heard lots of talks on Fano varieties all this week, and probably next 2 weeks as well. However, there is a fundamental question. I think people didn't even think about it before 2010. That was, how about we have a modular theory for Fano varieties? I mean, the reason people didn't think about it is there are some very simple examples to kind of imply that such theory doesn't exist. I mean, you just think about this example. This is just the example of degenerate smooth quadrics to the quadric over one cone singularity. So the typical, I mean, if you specialize to dimension 2, then it's just P1 cross P1 degenerate to the point over a Corning curve. So, I mean, if you want to construct a compact modular theory, you have to allow singularities. And the A1 singularity is the most mild singularity you can think of. So from a global theory, it seems that we have to allow this kind of object because it's very mild singular. It's quadrics with one A1 singularity. But however, we also have to allow this kind of object. But if you think about this family over A1 map to, if there is a modular stack, you map to your modular stack. Basically, it's like the puncture disk is mapped to a point, and the closed point, 0, is mapped to another point. So somehow this implies that if I want to allow both of these two objects, then the modular space won't be Hausdorff, and the point that corresponds to a smooth quadric is not going to be a closed point. This is pretty bad. So in other words, we have to cook up a theory if we want to get a moduli to remove this object, to remove this quadric A1. I mean this cone, this quadric cone. I mean we have to have a theory, and this theory has to be like intrinsic. And for a long time we just don't have such theory. However, I mean, the complex geometers really inspired us. I mean, you already heard this from Buxton and Johnson's talk, but let me just very quickly review the history. So for complex geometers, I mean, they were very interesting to study the Einstein metric, well, for differential geometers, they were very interested to study Einstein metric. And if you are complex geometry, if you are Kähler geometry, of course, you put the Kähler condition, then you are trying to study the existence of Kähler-Einstein metric. This question was originally posted in Kähler's original paper when he invented this notion of Kähler metric. And it became popular again by the advertisement of Calabi in 1950s. So basically, Kähler-Einstein metric, you already see this in the previous talk. It's just some metric satisfy that the rich omega is equal to lambda omega for some Kähler form. So the lambda here is some constant. But if you look at the class of both sides, no matter which Kähler metric you start with, the rich omega, the class is always the minus kx. So in other words, if you look at this equation, you know that depends on whether lambda is depending on the size of the lambda, your kx also should be either ample or anti-ample or just zero. So in the case that when kx is ample or trivial, so in other words, lambda is -1 or 0, we know that the Kähler-Einstein metric always exists. Especially when lambda is equal to 0, this is a consequence of Yao solution of the Calabi conjecture. So it's a really deep result. However, when lambda is equal to 1, so that's a Fano case. I mean, historically, people already know that there is some obstruction. For instance, one obstruction was mentioned by Buxon, that the automorphism has to be reductive. But of course, we know Fano varieties whose automorphism is not reductive, like a P2 Blapple point. So in other words, not every Fano manifold has Kähler-Einstein metric. Then you are, of course, the next natural question you ask yourself is when the Fano variety does have a Kähler-Einstein metric. And in 80s, Yao already had some deep reasons to believe the existence of Kähler-Einstein metric should be equivalent to some algebraic stability condition. But in his time, there was no good algebraic stability condition available. I think the one available to him was the Chow stability. I mean, the asymptotic Chow stability. But he also had some reason to see that might not be the right one. So, however, Tian in 1997, he proposed a condition which he called K-stability, and which I'm going to define all this later. But Donaldson realized that actually this definition of Tian's definition of K-stability can be formulated in algebraic terms. So in other words, Tian's condition was really an algebraic condition. And now this is a theorem, I mean, that a Fano variety, I mean, I think Buxon and Janssen mentioned the manifold case, but actually for Fano variety, in the Fano case, we even know the stronger that for variety, so we allow to have some singularity, X has a Kähler-Einstein metric if and only if this algebraic condition holds that X is K polystable. So next I'm going to define what K stability is, and I want to, as the entire lecture series, a large part of the lecture series is trying to unwrap this definition. So, as I said, that basically the K-stability of Fano varieties actually provides a subclass of Fano variety with good moduli theory. So you should regard this as if we want to construct a moduli for vector bundle, you should be stable vector bundle. So if you want to construct a moduli for Fano variety, it should be K-stable. And I wrote a book on this, which was published on, about 2 months ago. I think in US, when you write a book, you go everywhere to have a book tour. So this is one of my book tour lectures. Okay, so what's K-stability? Actually, the K-stability was given to algebraic geometers by complex geometers like Tian and Donaldson and the early 2000s. However, for a long time, we just didn't have a good understanding of it. I mean, there were relatively small number of people working on it because the notion was just very hard to digest. So now you can see one of the reasons why. But let's first give me the definition. So I start with the Fano variety X, and this notion already appeared in Matthias' lecture, that we look at the test configuration, which is just a GM equivalent of degeneration of XL over P1. So in other words, I have a family of XL over P1 such that only outside the special fiber, this is a trivial family. So it's trivial outside the special fiber. But on the special fiber, you might have some degeneration. So outside special fiber, you just got the X and the minus KX. But on the special fiber, you might have something more complicated. And then we just define this Futaki invariant. I mean, this invariant is looks slightly different with what Buxton defined, because in our case, our polarization is minus K. So our formula is slightly simpler than theirs. They were thinking about the general polarization, then the formula will be different. But when the polarization L is minus K, then the formula looks like this. So, I mean, if you first time say this, that's fine. Just remember this is some intersection, the top intersection of the L, which is parameterize the polarization minus K. And then the second top intersection of L together with the relative canonical bundle. So, I mean, it's not important to completely remember this number for now. But then we have the definition of stability, that if X is K semi-stable, if and only if that the Futaki invariant is always non-negative, and similarly, it's K stable if it's always non-negative, and the equality only holds that when the family is completely trivial. And the K polystable holds is that first it's semi-stable, and the equality holds when if you forget the GM action, the family is trivial, but actually I allow the GM action acting on the non-trivially acting on X cross P1. So the difference is in a K-stable case, I don't have the GM acting on my X, but in the K-polystable case, the GM might have a non-trivial action on the product. So that's what people call product test configuration. So let me compare this with GIT. I mean, because that's how historically, how people first try to understand the K-stability. I mean, there is certain obvious similarity. It's some number, whether it's it's obvious similarity with, for instance, like a Hilbert-Mumford criterion. But there is significant difference. So the first difference is that the X we consider is all the kind of the abstract degeneration of X. So it could live in an unbounded family. For instance, if I just think about the degeneration of P1, the central fiber could be, I just blow up higher and higher. So it's not in a bounded family, right? If I have a P1 cross P1, I just blow up the 0 and I blow up the GM fixed point again and again. It just go higher and higher. So this is significantly makes the problem significantly harder. Because for GIT, or in general for geometers, when we used to work in a finite dimensional space. But this question is really for some like unbounded problem. And even if you think it's similar to GIT, I mean the reason is this number can be regarded as the weight of some Lie bundle which defined over the Hilbert scheme, and then the GM action on the central fiber of the Lie bundle over the central fiber. So this looks very much like a GIT problem. However, this Lie bundle in general is not positive, unfortunately. So when we do GIT, of course, we do GIT for ample Lie bundle for polarization. If your Lie bundle to start with on Hilbert scheme is not ample, then the GIT just fails. So these are the two main difference with GIT. But actually, the even deeper thing is that to study the K-stability of Fano varieties, GIT is not the right perspective. The right perspective is a minimal program. And that's what I'm going to explain you. That somehow we should we should really regard this problem more like a minimum program type problem instead of a GIT problem. So let's first look at one of the early results proved using minimum program. So, when I define test configuration, I consider all the possible degeneration of X. But Chili and I, many years ago, we proved that instead of all the test configuration, you only need to consider something called a special test configuration, which means that the central fiber here, this central fiber for your special test configuration itself is a KLT Fano varieties. So for instance, if you think about degeneration of P1, you only have a degeneration have a P1, then you might blow up more. But all this further blow up, the special fiber is not a KLT anymore, because KLT will imply its analysis is normal. So in other words, we only need to look at the normal or even smaller class of KLT degeneration. And the reason is that basically we show to start with any test configuration, you can have a MMP process to produce a new test configuration, which is special, which has the property that the fiber is KLT. And then the photonic environment also satisfies this inequality. The D is basically just some degree of the base change factor. So the upshot is, for Bayesian geometers, if you start from a family, it's very natural for us to run minimum program to make your family simpler. So if you start adding X, it's somewhat natural for us to run MMP to get this special test configuration. But the upshot is, along this process, the photonic environment is actually always decreasing. So because we only need to look at the psi of the photonic environment, then we can just concentrate on psi of this type of thing. And if you just plug in the photonic environment, the formula of photonic environment into the special case, then just boil down to this much simpler formula. So it's just the total self-intersection of relative canonical bundle, and there's a psi there. And then you just ask yourself whether for any such special degeneration, this number is positive or not. However, it's still very hard to determine all the special test configuration once you go up to dimension 2. So even for P2, this is a challenging question. I think it's recently solved, but it's only recently solved. So it's really hard to, even for simple Fano variety like P2, to completely understand all the special degeneration. Anyway, I think this result represents an earlier evidence that MMP plays a deep role in K-stability theory. And also, it's first among a series result which I'm going to tell you that basically to test K-stability, the original definition from Donaldson Tian was to test all the degenerations, but we can work on different class of, here we can just look into all the special degenerations. That's enough. And later we will look at the other classes. And it's a deep result. I mean, there are a bunch of different results to show all these different characterizations are equivalent to each other. So here comes the next one. It's called Dean stability. So actually, Berman noticed that we can, for any test configuration, instead of photonic environment, we can define something called a Dean invariant. So the Dean invariant, if you compare to the photonic environment, there is still this top intersection, but there is no second intersection anymore. It's replaced by some low canonical threshold type stuff. So here the D is just the L is trivial outside of the central fiber. So the K over P1 plus L, you got some divisor supporting on X0. Then you just put this D here, and then you look at this number. Again, this looks like a very strange number, I agree. But at least when you have a special test configuration, you realize that if you have a special test configuration, then L, you can just choose it to be the minus K. And D is 0. Then the LCT here is precisely 1. Then the number again specialized to the self-intersection of minus K power to n plus 1 with a psi. So in other words, if you work on special test configuration, Dean is actually equal to photonic. And then you can, of course, use DIN to define all the stability notion as the similar way as a K-stability. But Fujita, I mean, he mimicked the proof for Futaki invariant, but applied it to the DIN invariant, and also show that to test DIN stability, it suffices to test also on the special ones. And we know on special one, DIN is equal to Futaki. So particularly, we know that although DIN stability, this notion looks like a new notion, but it's essentially the same as K-stability for Fano variety. I would say actually the later development of the theory actually all builds on DIN stability, not really on K-stability. But somehow here we show that they are equivalent. And the advantage for DIN stability is that, I mean, now it looks less like a GIT invariant, because if I have a family of test configuration, this number is not actually a constant. It's not a weight of some lie bundle. However, this number is, of course, very much like some invariants which MMP people care about. So somehow, if you say this invariant, you will probably, it becomes more natural for you to say that we probably should use the minimum program to study this instead of GIT, and that was the story. So now I want to go further deep. Go deeper to explain that we can also study K-stability using valuations. This was already also mentioned in Buxton and Johnson's talk, but let me just remind you, I mean, I also set up some notion. So if I have some test configuration, I look at any component of the special fiber. Then this component will give me a valuation over the field of Kx, but the X is bidirectional to X cos A1. So it has a subfield which is of Kx. And then I can just restrict this valuation to the to my subfield. And unless this Y is given by the trivial component of X cross 0, then in other cases, it will give you a divisorial valuation of the forms C times some odd E. E here is some divisor lives on a birational model of X. So it's a divisorial valuation over X. So it lives on a birational model. And then we can define these two quantity. The first one is log discrepancy. I think this we already see many times. So, and we know it's always positive because I assume my X is KLT. So in my lecture, when I say Fano variety, I always mean KLT Fano variety. But the second quantity is more mysterious. It's the expected vanishing order. I mean, if you have a good feeling of Buxton and Johnson's lecture, then you know that this is somewhat related to the energy functional. But this was actually first found by Fujita and in some sense, I think by brute force. If I hope he agree with me. So I mean, he's here. You can check with him. So anyway, this expected vanishing order is given by that. So if I look at the minus Kx, I ask myself, like how much Kx, the section of Kx vanishing along E, and of course Kx might have many sections. So I just look at the average vanishing order, divide by the number of the sections, and then I let the Kx, the power of Kx go to infinity. And then I take the average, it's precisely this number. So here, this comes to one key observation. I mean, the proof is not hard, but you have to notice this, that if X is a special test configuration, non-trivial, then I have only one special fiber, X0, right? Because special means the central fiber is KLT, so it's normal, it's irreducible. So I just got one divisor with some multiplicity before. Then the Futaki invariant can be computed as A minus S times this factor. So somehow you can really read off this Futaki invariant by A and S, and this is in a special test configuration case. So then here comes the Fujita-Lee criterion that if I check the left-hand side, are notions which are originally defined by looking at all test configurations, and now we can only check them by just looking at the valuations. And essentially one direction I already proved, because to look at the left-hand side, I only need to look at the special test configuration. But special test configuration, you have this E. You cook up in my previous slides, this E here. I think this previous slide. And then you compute the photonic invariant. It's just A minus S. So then you assume A is larger than S. Then, of course, all the photonic invariant is positive for the special test configuration. Then the photonic invariant is always positive because the first reduction result. So now we want to say the other direction that, so other direction says that if I know my photonic invariant is positive, so in other words, if I know the A is larger than S, for those E which arise from test configurations, that A is always larger than S. So I'll explain how to prove this. But let me just mention that to compare A and S for all the E, that's actually much more computable than compare the photonic to look at the size of photonic invariant. So this gives us a more computable calculation of K-stability. I'll talk about this more maybe in my third lecture. So, okay. So now let me go a little bit more. Should I do? Sorry, here it's okay. It's okay in room. Okay. Okay. Sorry, let me. Should I just unplug and plug in this again? Okay.
Is it attached down below? Should we put it on my computer?
Is it not coming back at all?
Now it's coming.
Oh, I can hold it up there. Oh,
This is what?
oh, you're taping it up.
Oh, it's down again. It's this part.
I think it's this part then.
Okay, so maybe.
Let's try one last time. No signal. Andrea, shall we try putting it on your computer?
Now it's come. Maybe.
Is it come back
Yeah,
again?
it's back again.
Do you want me
Okay,
to
so
hold
then
it in?
We just don't do anything.
let me just secure it. Yes, duct tape can fix anything.
And then Christopher has the duct tape.
I'm not on loop.
It's not on Zoom.
Well, that's
That's a different story.
Okay. Should I? Sorry. Maybe at some point I log out from the room. I mean, sorry. I should have. Maybe I can try from here. The password.
Okay, I can get the password. Do you have this? This is the password.
Okay, yeah, I have the I think I have to share this again. Mm,
Okay. Do you want me to,
yeah, maybe.
want to do it here?
Sorry, I have to first become a plan next time. Okay. Okay, now I can share.
Let me get ready to share,
Mm.
just in case. Should I share?
Yeah, I think I gave you permission. Yeah, you're back on two. Okay.
Okay, cool. Yeah, okay, thank you. Okay, so I didn't shake hands. I tried.
That's the other one. Yeah, might just need a different.
Should I share with my computer?
Everything, yeah, I'd say probably try a different computer.
I'm going to share it with the cable. The cable's in my back.
It's back again, so but I don't know how long it will last.
Wanna give it a try?
Well, I can give it a try.
Okay.
Okay,
No.
okay, maybe forget it. It's not going to.
Okay, let's just do it on my computer.
Assuming you get it.
Yep, I do, but I need to put this in my machine.
You.
Oh. I would have sorry, I'm gonna go.
To put that in.
Which one? Which one is those?
I don't know if I'm the host right now.
I'm not. I'm
I'm
not.
the host right now. Christopher, am I host right now? Christopher, am I host right now? Christopher, am I host right now? Christopher, am I host? Christopher, am I host? Christopher, am I host? Okay. Okay, so do I have your slides?
I don't. I don't.
And you have to,
I have to send you.
no,
I can send you my slides. Sorry.
I mean, I can. I mean, I'm hooked up with you. Yep. So I should share with, well,
I don't know why it keeps dropping out.
it's dropping out.
Yeah, it's not straight.
Okay. Let me go to advanced with the cable.
If there is a participant by the last name of Choi who's staying in Corbett 318, please come find me.
Oh,
I
wow.
just sent it to you.
You sent
Your
them.
Gmail.
Oh, in my Gmail. Okay. Instead.
Oh, this is your not from.
Yeah, I'll be there.
Oh, yeah, here it is. You sent me the file.
Yeah. Did you get it?
I got something from you, but I don't see anything there.
I thought it's maybe let me send it on here.
iPad, it says, but there's nothing there. But I think we should just be able to connect with the, I should just be able to share. I didn't get the thing that says I accept being a panelist. Oh, wait, am I a panelist now?
Showed you as a panelist.
Okay, great. Okay, then let me just share his notes. Let's stop share and share again. Share via cable. Share. So where is your iPad? That's the thing.
Yeah,
Oh, you're not attached. Are you
No,
attached?
I
Okay.
think I'm attached.
Is that your iPad?
Yeah, yeah, maybe you, I think this is my.
Okay.
This is my iPad, yeah.
Okay,
Because,
Here?
Yeah.
You have
Maybe-
to open it.
I
Just
have-
open it.
Okay,
There it
okay,
is.
Okay,
Now, unfortunately, it's not on the whole screen. Let me see if I can maximize it.
yeah, I think it's looking good, actually.
It looks good?
The screen is not,
It's not maximized.
yeah, but maybe it's okay.
Does that help?
Yeah, okay, this helps.
Okay, oops. Shoot. Okay,
Okay,
you want to just use that?
okay.
I don't know if you can make,
Sorry, it's gone.
it's gone now.
Oh, now it's bad.
Okay,
Okay.
so maybe, does that change this? You have to change it on your screen, I think. Yep.
Okay, okay, thank you. Yeah. I mean, the screen is gone again, so yeah, I think there's,
Anybody have, wanna ask if anybody has another connector?
Yeah, anybody have a connector?
And this shouldn't be.
But it was both computers, so it's not the computer, it's the connector.
Well, it's the third connector.
Yes. We have a different dongle here.
Then can we get it up on there so that this isn't hanging off the side?
Could you hold this?
sure.
Okay, so oops, get that away. Okay,
Okay.
Pretty sure it's the connection, like, see how this is loose?
maybe switch these. Oh, no, because then we'll lose connection
You
with
have
that.
connected
No,
this
it's
side.
on one side. We can share again, we can switch them, but then we're not connected to him. But I mean, it wasn't working on his either, you know what I mean? Now put the cable over there. Oh, it's over here. Okay, now let's share again. Stop share. Now we're gonna share. Allow.
Oh, yeah.
Okay, where's the ability to, okay, we'll stop share and share again. Share. Via cable. Share. Okay,
Okay.
so where's your iPad?
It's not connected. Maybe I can just work on the slides. Oh, well, you don't have a slide, but the iPad is.
Okay,
I have to
you
find-
want me to get the slides?
I think you can just try to find my plan, because
Did you send them again?
I didn't, because I don't know how, I mean, for some reason,
Oh, here they are.
Okay,
Here they are.
okay, okay.
Is it on
But-
Zoom?
yeah.
Christopher, is this on Zoom? Okay, so now we have to just make them
Okay,
view. Come on.
You just leave it at that. Don't have to do it.
Okay, you want to just use it like that?
okay, yeah.
On Zoom, it's looking good.
Yeah.
We just come to,
Maximize that window. Oops. I don't know how to make it bigger. Upset on the right hand side. Make this bigger here. Okay,
okay, thank you. All right. Okay, I think we are good now. So, since we have a free afternoon, so I can go, maybe I'll be over time. So, and then actually I changed my slides for many different version. I hope this is my last version. but anyway, so where we are trying to basically digest. I mean, I think we don't know how to make it bigger, so. Yeah, there's a view, maybe. Oh, full screen, okay. Okay. I think it's slightly bigger. So I think this is the best we can do for now. Yeah. Let's just continue. Yeah. So basically, we try to understand this number Sx, and we try to approximate it by some finite level invariant. And so what we are going to do is we look at the H0 minus MKX, which is Rm. And we consider a basis type divider, which is basically have a basis of sections and sum of them together. And the scaling it such as the dm is q linear equivalent to minus kx. So basically, I just choose a basis of choose a basis. I sum up the order divider and I scale it back, such that the scale after scaling is minus k. And then we can look at for any divider E, it induces a filtration Rm, just given by the vanishing order, right? Then I define SME to be the maximum one, to be the odd E vanishing along this basis type divider. And then one can easily see this is nothing but just the gradient, like basically this number. Oh, sorry, I don't have a pen here. This is this number lambda times the gradient. So if you have a vanishing M with, I mean, if you look at the order M and you have something like AM, the gradient dimension is AM, then you just sum up all this M times AM. Then we can similarly define a file level version is that I just look at the infimum of A over SME. So, and then one can easily prove the dual version that the delta mx, the infimum, is indeed that if I look at all the basis type divider, I compute the log threshold, the minimum of them. So somehow it's just this kind of special type of divider. I look at all of them. I can compute the minimum log threshold. And the crucial result proved by Fujita Odaka and Bloom-Janssen is that if you take the limit of delta m, it's going to be some number delta x, which is just the infimum of A divided over S. So remember, the stability is characterized by A minus S for all E. But we can just, instead of minus, we just divide it. And then we'll look at the infimum of this. Now we know that the delta x is larger than 1 if and only if x is k-stable. So somehow we have a quantitative way to characterize how stable your Fano variety is. Even it's not stable, I mean, the delta x gives me a number, quantity, so that I can tell this x is how unstable it is. This plays a central role. And the fact that the delta x is a limit of this kind of delta mx, this kind of log threshold type of invariant, also makes us to be easier to compute it. So, and the fact that we only think about the basis type divider is actually some interesting fact which will also give us some advantage. Sorry, I don't know how to go to next page. Okay, cool. Actually, just works here. So now I want to introduce a somewhat technical notion in middle program, which is called complement. This notion was invented by Shortcroft, but not, actually I think for a long time, people just think about it as some like technical notion, but now it become a very central tool to study bidirectional Fano variety. So what's complement? The definition is easy. We just consider some divisor MD in MKX. I write this way because then I can say D is nearly equal to minus K, but require XD is low canonic. So basically you complete your Fano variety to make it local beyond. And one of the very deep result Burkhardt proved in his attempted to prove in his work of proving BAB conjecture is he proved the following result, which is actually absolutely crucial for us to develop the K-stability theory, is that there exists a uniform N, dependent on only the dimension X, such that all KLT Fano variety admits N complement. I mean, remember, all KLT Fano variety form an unbounded family. For instance, if you think about the Hilbert surface, you contract the negative curve, then they are all log-Hilbert surface. Of course, they are unbounded, but the Burkhardt theorem, which was Shirkov's conjecture, is that the uniform N such that you can, even for this unbounded family, you can complete your log Fano to be local beyond. I mean, for bounded family, of course, you can just then it's easy to get it. But the upshot is here, it works for this unbounded family as well. And then I introduce a notion which is standard in bidirectional geometry that if I have a low canonical pair, then I call LC place of a low canonical pair if that basically the log discrepancy for this divisor is 0. So the local LC place is some divisor over this X such that the log discrepancy of this pair is 0. Yeah, this. Okay, now I want to talk about some theorem. So as I said, I mean, there is this kind of there is kind of this test configuration, and there are this divisor, and we know special test configuration correspond to divisor. But you might ask, well, what kind of divisor correspond to test configuration? So actually, there is a precise characterization of a class of test configuration which is more general than special. So special means this part is PLT. So X0 is KLT. So here I only require X0 is semi-canonic and irreducible. So in other words, this guy is LC. So we call this weakly special test configuration. So for all this test configuration, the divisor arises from this test configuration is precisely the LC place of some complements. So the left-hand side, you have this very geometric class of divisor, which is LC place of some Q complements. And you know they precisely correspond to a class of test configuration. And then the next question is, of course, will be whether this class of divisor, you can compute the delta using them. And the first is the somewhat simpler statement is that at least when delta x is in this range, remember the interesting range is when delta is less or equal to 1. So we can even go a little bit up, and then we know for delta m, the delta m we are interested, they are all computed by some LC, by some EM, by some LC place, when at least when m is large enough. And then we can apply Burkhardt theorem to say that actually if LC place is a LC place of a Q complement, it's actually an LC place of N complement. The N is this uniform N give to you by Burkhardt or by some like a slightly different versions of Burkhardt theorem. And also now in the second, under this assumption, we know that the delta x is indeed here we say the delta m, but actually delta x itself is computed by A over S. But here we can even assume that the EM are all the LC place of a fixed complement. So originally the EM might be for different complement, but actually we can to assume there is one complement works for all of them. And then we actually show that if you have a family of Fano variety, then the delta function and this is the minimum between 1 and delta, is a constructible and the lower semi-continuous function. Here, constructible is for Tarski topology. So if you look at the delta, I mean, there might be an open set which is 1 or above. Then there is some closed set which is less than 1. So in other words, K semi-stability condition is an open condition. So, in general, if you have a modular problem, usually it's not hard to prove the stability condition is open. But in the in this question, the proof of the K semi-stability to be open condition is actually quite tricky. So I want to discuss the proof a little bit. I mean, the proof of the first two facts are actually relatively simple. It's straightforward. So in biogeometry, there is something called a two-ray game for Fano variety if the Picard number is 2. Here I call something called a two divider game. So that's for family. But now if I have one central fiber have 2 components, then I call two divider game. So then if I start with the LC place of XD, I can just make a trivial family to be this one, to cross A1, and I add the special fiber in. And because that the E is the LC place, actually I can extract the E1, which is basically the E, the weighted blob of E under the X0. Then this is going to be an LC place for this pair. So I extract it, and then I run MMP to contract this one. I get this test configuration. So somehow I start with a family. I have this LC place. I extract it. Then I contract the Bayesian transform of the original special fiber. I just got this test. I just got this test configuration. So once you see this equivalence, the proof is at least the one direction is not hard. And maybe I'll skip the second part. So the second part says that the delta M is actually always computed by the LC place of some divider. And anyway, if you put 1 and 2 together, you already say that because delta X is always not 1 and 2, I should be 1. Okay. So if you put the 1 and the 4 together, so it's 4, implies that the delta X is computed by. Okay, maybe I'll stop here and I mean I have maybe 3 slides. I mean we can continue tomorrow. Yeah.